iToF2dToF, a robust and flexible representation for data-driven time-of-flight imaging. Direct time-of-flight imaging systems, or dToF systems, are depth-sensing cameras composed of a sensor and a pulsed laser that illuminates the scene. To estimate depths, dToF systems emit a light pulse and measure the time of flight of the pulse to the scene and back to the sensor. Each dToF pixel encodes depths in the time delay between the emitted pulse and the received signal. For a given scene, to compute the round-trip time of the pulse, dToF systems use ultra-fast sensors to capture a video of the light pulse as it propagates through the scene. These videos are referred to as transient images or dToF images. A different modality of ToF imaging is indirect time of flight, or iToF. iToF systems illuminate the scene with a sinusoid-modulated signal. The phase shift on the returning sinusoid signal will encode depths. Instead of relying on fast sensors to measure the phase shift, iToF cameras correlate the sinusoidal signal with another sinusoid at the same frequency. By repeating this measurement with additional shifted reference signals, we can compute the phase shift and extract depths. Finally, to further increase accuracy, we can also measure additional frequencies. iToF cameras can enable emerging 3D applications such as augmented reality and robotics due to their low cost, high spatial resolution, small form factor, and their solid-state implementation. However, they face important challenges. First, these cameras often operate in low SNR settings due to practical constraints such as low power and low exposure time. And second, they suffer from multipath interference, which is caused by indirect light paths hitting the sensor. If there is no MPI, that means that the phase shift of the received sinusoid only depends on the direct reflection. In the presence of MPI, however, the phase shift of the returning sinusoid not only depends on the direct reflection, but also on the multiple indirect reflections. If we zoom in the MPI corrupted signal, we can see that the phase shift no longer matches the time shift of the direct reflection, leading to depth errors. One common approach to overcome these challenges is to first denoise the iToF images and then remove MPI. To remove MPI, many solutions have been proposed, and most of them involve estimating the transient image as an intermediate step. Finally, depths can be obtained from the transient representation through peak finding algorithms. Recently, a different iToF imaging pipeline has become the state-of-the-art, which relies on data-driven models. We group these new approaches into two categories, depth-to-depth and iToF2depth. This grouping refers to the input-to-output representations used during training. From the iToF images, depth-to-depth models pre-compute MPI corrupted depths and use them as the input to the data-driven model. On the other hand, iToF2depth models directly input the iToF images. Finally, they both use depth images as the final output representation used for supervision during training. Current data-driven iToF models perform well. However, it is sometimes challenging to provide the correct depth supervision because ToF data can encode depths differently depending on the scenario. For instance, in a scene with diffuse MPI, the correct depth is encoded on the maximum peak of the transient pixel. But in the presence of semi-specular surfaces, like the glossy floor in this scene, the correct depth is encoded on the first peak, which is not always the maximum peak. Alternatively, consider optical crosstalk. Optical crosstalk can arise when you have a bright object near the sensor and a dark object farther away. Due to lens interreflections, the signal from the bright object may leak into the dark object pixels. In a real-world scene, this will often happen in high-contrast regions at depth discontinuities. The high-contrast regions will experience high crosstalk, leading to incorrect depth estimates. Finally, consider depth discontinuities. What should we choose as the correct depth, foreground or background? In a robotic navigation application, you may want to choose the foreground to dilate the object edges, which might improve obstacle avoidance. On the other hand, in a robotic grasping application, you may want to choose the background depth for edge pixels to ensure a tight grasp on the object. Overall, performing depth supervision for all these scenarios is challenging and somewhat ambiguous. In this paper, we propose iToF2dToF. Like previous data-driven iToF models, we begin with the captured iToF frequency data. The data is input into a data-driven model, and instead of predicting depths directly, our model interpolates and extrapolates the iToF frequency data. The dense frequency representation is then used to estimate the dToF image. Finally, we can extract depths from the dToF image through rule-based peak finding algorithms. Here's one of the estimated transient images. This scene exhibits a specular reflections on the TV, which leads to a low amplitude direct reflection component as seen in the recovered transient pixel. This causes erroneous depth estimates in traditional and data-driven iToF methods. By using simple peak finding algorithms, iToF2dToF can recover a high-quality depth map. In this result, we can observe the optical crosstalk when the light signal in the transient image hits the planar target. The signal in the high albedo foreground regions leaks into the low albedo background pixels inside the number 2. This leads to incorrect depth estimates for the background pixels. iToF2dToF produces the correct depth image by using the prior knowledge that crosstalk errors are significant in high contrast regions. So, in those regions, the correct depth will be the second peak in the transient. To further quantify the benefits of iToF2dToF in the real world, we also performed experiments where we had ground truth depths available. To capture ground truth, we first acquired an empty scene like the wall above and estimated ground truth depths using traditional methods. Then we captured the scene a second time with objects placed in it. The depths from the first capture give us partial ground truth for the second capture. An iToF2dToF model that only estimates a transient image with a bandwidth of 100 MHz experiences significant depth errors due to MPI. However, as we train models with a larger bandwidth, the MPI errors reduce substantially. Like recent data-driven models, iToF2dToF provides significant MPI error reduction over traditional methods and can outperform a data-driven model trained to directly predict depths, even at extremely low SNR. We note that the phasor baseline shown here does not perform any denoising and is shown for illustrative purposes only. In summary, we incorporated for the first time the transient image representation into the data-driven iToF imaging pipeline and showed that it can be a useful representation in different depth sensing scenarios.